the discussion there.
Yeah, thank you.
Okay, excellent. So our next speaker then is going to be, well, I'm not sure I'm going to say this quite right, but Nikson Ferreira, and he'll be talking about verifying and implementation of the well-clear avionics specification.
Yes. Hi, I am Nikson. Master degree student at the University of Brasilia, supervised by Dr. Marcelo Ricon and Dr. Mariano Moscato, and this work also consists with the collaboration of Dr. Laura Titolo. Today, I will present to us a verified float point implementation of correct well-clear definitions. Floats are the most common computational representation for real numbers. That is, a finite representation for an infinite domain. What leads that not every real number could be exactly represented. This difference between the ideal real number and its finite representation is called round-off error. This is not the unique problem of this domain. We also have runtime exceptions, such as division by zero, not a number, etc. Writing correct float point programs could be really challenging and particularly dangerous for safety-critical systems when a misbehavior could lead the same that occurred in the Patriot missile 1991. A round-off error made it unable to track and intercept an enemy missile, leading to 21 deaths. At least it was a long time ago, right? 2007. Automatic Dependence Surveillance Broadcast, the next generation of air traffic management, required in aircraft above 200 passengers in America and in Europe since 2020. However, this technology has a cons. It uses the old Zcash transpose that only reserves 35 bits to represent latitude and longitude. So there is the compact reporting positioning algorithm to improve the precision of this representation. However, in 2007, Australia Air Service reported that this algorithm decoded a position with a small error, just 220 nautics miles away from the actual position. Round-off errors could be really dangerous. Our safety-critical application is in the context of the integration of unmanned aircraft in the civil airspace. In the past few years, several organizations have been trying to develop and create solutions in that way. One of them is Daedalus, the detect and avoid alerting logic for unmanned systems developed by NASA. One of its differentials is its correctness and safety properties are formally verified using real arithmetics, and it was integrated as minimum functional operational standard in RTCA, providing three main features: conflict detection, maneuver guidance, and alerting logic. However, numerical issues could affect the computed result, so a testing basic approach was used to check the actual implementation. However, safety critical applications such as Daedalus require the higher level of assurance. So our approach automatically extracts a C source code from the ideal real specification. This C code is instrumented to, whenever a divergence in the control flow may occur, emit a warning. And it's annotated with contracts claiming this behavior and bounding the round-off error of this implementation, being externally verifiable. So this approach uses several different formal methods tools, such as PVS, Interactive Theorem Prover, Precision Analyzer and Code Generator for float point programs, and Pharmacy, a collaborative framework for static analysis in C source code. These tools are integrated in a toolchain that, inputting a PVS real specification together with concrete input ranges, precisely generates the instrumented C code annotated in SSL language and PVS round-off certificates. Then, Pharmacy read this generated C code and the contracts annotated and generate verification conditions. These verification conditions are automatically proved by PVS using the previous generated round-off certificates and ad hoc strategies. So at the end, we have a float point implementation that has formal guarantees of its round-off error bound and Emit alert whenever a control flow may occur, and automatic. That is, no expertise in float point or theorem proof are required. So, can we apply this system as it was in our case study? Not as it is. Our case study has some kind of complexity, such as high order specification, intensive use of predicates, and higher number of functions calls. So we cannot apply it. So we extend this approach, rewriting the high order declarations in fish order and conditionally slicing this specification, turning it manageable to the toolchain. So the standard toolchain now begins with a translation from high order declarations to first order, then proving the functional equivalence between then conditionally slicing this fish order specification and proving the equivalence between them, and for each slicing, apply the same integrated toolchain. In our case study, we divided the well-clear model based on the relative velocity in 6 slides as shown here. And to illustrate the application of the integrated toolchain, we will use this TCPA function, the time of closest point approach, a function that is in specification of DIDOMS, that receives the relative distance and velocity vectors, and if the norm squared of the velocity is greater than 0, return minus the projection of relative space vector in the relative velocity vector over the squared of the norm of the velocity. Otherwise, both Vx and Vy are 0, and then return 0. Inputting it to Precisa generates two functions. The first one is purely symbolic, and the second one is with concrete values. Here we have the instrumented TCPA function, and here we have the annotations. This first line here just is the same TCPA declaration over the reals, and just a question of notation here. Everything boxed is a float point. So what Precisa accurately does is replace the original guard for more restrictive ones that takes in account the round-off error. So here, instead of greater than 0, it's greater than a symbolic error variable e. Then, if it's true, return the first brand. Otherwise, instead of just returning 0, it checks again a more restrictive version of the else, then return 0. Otherwise, it may be a control flow divergence, so emits a warning. Here we have the float point counterpart of TCPA, just replacing the real operation by float point operations. Here we have a predicate that states there's no control flow divergence, that is a stable path, and basically it checks if the guard is evaluated over reals and float point has the same value. Then finally, the contract, it requires as preconditions that the symbolic error variable is positive and finite. Then ensures as post conditions that if the result is not a warning, then the result of this instrumented implementation is the same of the not instrumented float point implementation, and ensures that if the result is not a warning, implies that if the symbolic error variable is a bound for round-off error of guard expression, then we are in a stable path condition. I mean, there is no control flow divergences. The second function generated by Precisa is just calling the previous one, but with a concrete value for the symbolic error variable calculated by Precisa. And as contracted we have here, if the variables, input variables remain the input range, and the input variables are just rounding using rounding to nearest the ideal inputs, then the implementation round-off error is at most this value calculated by Precisa. Then once this is generated, we read it from a C and generate verifications conditions that looks like it or it. And so at the end, we are able to analyze the whole well-colored module of Daedalus, and the conditional slicing make the process manageable to the toolchain, and also produce more simplified versions verifications conditions. During this process, which covers several opportunities of improvement that were reported and fixed. And in this work, we use a new axiomatic floating point formalization that, besides of improving the type check time in a factor of 5, also now support special values, such as not a number in infinite. However, it impacted the previous one's strategies that were not long usable. So as future work, we aim to improve the automation degree of our approach, automatically slicing with a using hint and generating the equivalence lemmas, and also maintaining and generating more PVS strategies. So thank you very much.
Thank you, Nikson. I'll start off the question and answer session since we have time. I don't feel bad monopolizing some of it. So where did you get the implementation you started with to do some of the verification work? Right, was that directly from the did you start with just the specification, or did you start with some existing implementation that you could modify? What is the kind of path to getting the implementation that you modified?
We start with the high order specification of diodes that were previously developed. Then we translate it for first order, then continue the things from here.
And is that specification being used anywhere? I know you did some of this work at NASA. Is this like proposed for some kind of standard for unmanned aerial vehicles? Do you know what the status of the specification is?
Besides of the specification, there is a C and Java implementation of this specification that were manually translated for it. So this is the current status of it. I don't know if I answered, but
okay. And there's a question from Mariano. Do you want to ask it?
Hello. Yes, I just wanted to clarify, maybe help Nikson answer. So the specification is part of a module, yeah, and in fact, they some people at NASA, they developed this specification and they manually created an implementation in C and in Java that is part now of the standard for the detect and avoid, for one particular standard for the detect and avoid. So yes, you may say that this is a all the work that they did is in fact as part of our reference implementation now.
Cool. Yeah, that makes a lot of sense. Okay, so I'm going to move on just to keep ourselves on schedule. There's some other questions in the Slack that Nikson and Mariano you could look at. So our next speaker, and if you could unshare your screen, that would also be appreciated, Nikson. Perfect.